Now, today and in the following lectures, we delve ourselves into the discussion of the thermal properties of matter. Very interesting properties. Of course, temperature and heat are the nuances that have to be understood properly. You know it from before. It has been discussed in junior classes that temperature is a relative measure. It indicates hotness or coldness of a certain body. We find that there is a heat transfer from or to another body or surroundings, and this happens like the water flows from a higher level to a lower level. Electric current flows from higher potential to lower potential, etc. Similarly, the heat transfer takes place from a higher temperature to a lower temperature. Both may be high, both may be low, both may be in between. So, to distinguish heat from temperature, heat is the form of energy. Like kinetic energy, potential energy, this energy, that energy, heat is also a form of energy which is transferred between two or more systems, well-defined systems, or a system and its surroundings by virtue of the difference of temperature. If there is a difference of temperature, then heat will be transferred. If there is no difference of temperature, no heat transfer can take place. The system international unit of heat is Joule. Okay? Earlier it used to be in the CGS system, arcs, etc. Well, the SI unit of temperature is Kelvin. Remember, look, I write Kelvin with a small k here and represent it by a capital K. Also, one of the things which we have been knowing and which we know is the Celsius scale of temperature, where which is also very closely related to the Kelvin temperature. If I add a Celsius temperature 273.15, then I will get the Kelvin temperature, that scale. So what? If we supply heat to a body here, what will happen? First of all, temperature will change. And there are many other changes that may take place. There may be an expansion, etc. Some cases there is not an expansion, it's otherwise. For example, in the case of water, the anomalous behavior of water at around 4 degrees Celsius, change of state from the solid to the gas, solid to the liquid, liquid to the gas, gas to the liquid, liquid to solid. Also sublimation, where it appears that change is taking place from solid to gaseous state. Camphor, etc. Okay, now let us discuss the measurement of temperature. Temperature is measured by means of thermometers, which are analog or which are digital. Okay, so what happens and why? So, with the rise in temperature or a fall in temperature, many physical properties of materials, they change sufficiently. Sufficiently means we can just see that there is a change. Okay, we can observe that there is change. Okay, which we can naturally measure, and this can be made any of these properties of the materials can be made as the basis for construction design of thermometers. Okay. For example, one of the thermometers we have known from long time is the liquid in glass type, using either mercury or alcohol. Alcohol, something which is a finding and this thing is study and description by the Arab scientists, just like alchemy, and so alcohol is. However, this is banned for the Muslims among the Arabs. It is kind of prohibited. Anyway, it has to be used if need be in many device fabrications and device designs. For calibration of these thermometers, the relationship that should be there with temperature should be kind of a linear relationship. And if that linear relationship exists, then we just need two fixed reference points. These points normally are what we know as the point at which ice melts to form water, and the water boils to give water vapors. So this is what we know as 0 degrees Celsius and 100 degree. And between that, if there is a scale and we forget it into 100 parts or maybe more as is desired, and so that can be done, and that is a calibration which is essential feature of the thermometers. So we have some liquid like the mercury or some kind of alcohol, ethyl alcohol, etc., which give stable properties, and we can obtain the two definite points, which is in the Fahrenheit scale is 32 Celsius is the freezing point, and 212 degrees Fahrenheit as the boiling temperature. In the centigrade scale, we have 0 degrees Celsius as one reference point and 100 degrees Celsius as the other reference point. And when we see that 100 degrees Celsius this point and 0 degrees Celsius, which is this point, for the two, and draw a line, a straight line, then it appears that there is a linear relationship which exists between the two of them, so that it's easily we can obtain this relation as the Fahrenheit temperature minus 32 divided by 180, because there are bifurcations 180 over there, and Tc minus 0, which is Tc itself divided by the 100 divisions that we need to define the Celsius temperature, which is also known as, because there are 100 divisions, so that is also called as centigrade scalar temperature. The fixed points, they will always arrive at the same set of temperatures, but somehow the volume expansion of these liquids is somewhat there is found a deviation often with the defined theoretical value, and therefore they are not as good as the gas temperatures thermometers are. And gas thermometers, we take a gas which is a diluted gas. Diluted means that the density of the gas is not very high. It's not compressed gas, it is rather a diluted gas. And for all diluted gases, they behave like ideal gases. Okay. So a thermometer that uses a gas gives the same readings regardless of which gas is used. Why? Because all gases at low densities exhibit same expansion behavior. Okay? All gases at low densities exhibit same expansion behavior. Now, there are certain parameters which are pressure, volume, and the absolute temperature in Kelvin. These are some of the variables, some of the factors which define a given mass or a given quantity of an ideal gas, which is a diluted gas mostly. The gases have been explained in terms of what is known as the kinetic theory of gases, where we consider gases just like we consider the liquids and solids to be made up of molecules which have some kind of a cohesive force which is exhibited over there because of the negative energies associated over there, and all these molecules are supposed to be round objects. When I say round, I mean perfectly spherical. They are supposed to be very hot, and when they collide with each other or with the walls of the container, they exhibit the what we call perfect elasticity. So there is no loss of energy, and all energy is contained in the kinetic energy of these molecules. Okay, so they are found in all sides of the vessel in which they are contained, and the same pressure exists at all points on the whatever kind of container we have. So that defines the pressure. Pressure is defined in terms of the change of momentum. Also, that means it's average kinetic energy of the molecules that defines these things. Volume, of course, is not dependent upon that. Then we have the temperature, the absolute temperature. Okay, and when these things are studied through the kinetic theory of gases, we find the laws. For example, the Boyle's law. The Boyle's law which says that if the temperature remains unchanged, the product of P and V is a constant. That means P is proportional to 1 upon V, or it is a kind of X, Y is equal to constant kind of a relationship. So if we draw that, it will turn out to be something like this. Okay, so this is one relation which exists. There is another relation for these diluted gases which shows that if the pressure does not change or the pressure remains the same, then the volume of the gas is directly proportional to the temperature, or V upon T is equal to V1 upon T1 is equal to V2 upon T2 is equal to Vn upon Tn, and this is also a constant. This is called the Charles law. If you combine these two laws together for the diluted gas case, then we obtain what is called the ideal gas equation. I am going through very fast because the same thing has been taught to you or will be taught to you in chemistry. Okay, so I need not waste time over here. So we find that the product PV is equal to nRT. PV is equal to nRT, or PV upon T is equal to nR. Okay, here N is the number of moles in that given mass of gas, and R is the universal gas constant, which is equal to 8.31 joules per mole per Kelvin. It's universal in the same sense, like capital G is the universal gravitational constant, and similarly the gas constant, ideal gas constant, PV is equal to nRT, that R is also got to be remembered in your mind. R is equal to 8.31 joules per mole per degree Kelvin. Okay, so the ideal gas equation, which is true for diluted gases, for n moles it is PV is equal to nRT, where R is the universal gas constant, and if N and R are constants, then we see that PV is proportional to T. Okay, we design a constant volume gas thermometer, which means that the volume of the gas is unchanged, it is constant, it's not varying, in which case this D becomes a constant and we can say that T is proportional to T, or conversely we can say that T is proportional to T. So the temperature can be read in terms of pressure, which can be measured very accurately by means of various manometers, etc., which are at our disposal. We find that there is a graph which we obtain between temperature and pressure, and of course the equation is PV is equal to nRT when delta V is equal to 0. So the slope becomes equal to nR upon V, all of them are constants. Okay, and if I extend it like this, this meets the temperature axis at a temperature of minus 273.15 degree Celsius. Okay, now this could be, this is for one gas. If there are several gases, we can have curves like this, which all of them they will culminate, in case of all the gases, they will end up at this minus 273.15 degrees Celsius, which we call absolute zero. The predictions, this is a very long range of temperature, that this linear behavior is true, but on real gases the measurements deviate from values predicted by the ideal gas law at low temperatures. One of the important things which occur to us is that the gas no longer remains a gas. It will become, at low temperatures, it may become a gas, from a gas it can become a liquid, later on it can become a solid. However, the relationship is linear over a large range of temperature, and from the graphs that we get towards this absolute zero, it appears that the P will fall to zero. The P will fall to zero. The P will fall to zero, and P is explained in terms of the mean kinetic energy, the average kinetic energy of the molecules which constitute the gas, which means if P tends to zero, then the average kinetic energy also tends to zero, which means that the velocity of the molecules also goes zero. Okay, there is no motion of molecules, and therefore we can say that the molecules are in a condition of rest, everything. So this is taken as, this temperature is taken as the absolute zero, and this is the Kelvin scale of temperature in the name of honor of Lord Kelvin. Okay, and here the 0 degree Celsius is equal to plus 270.15 Kelvin. So Kelvin is the temperature in the SI system, in the MK system, and is one of the important units for that. Well, we have in a very fast manner, in a nutshell, explained to you as to how heat is different from temperature, how they are measured, how temperature is measured by the expansion of fluids, which may be alcohol, which may be mercury, and how the same thermometry can be carried out by the help of manometry, where the temperature is explained in terms of pressure, okay, in the constant volume gas thermometer. This is one of the important thermometers, where for most of the temperature, the linear relationship between the temperature, because I can draw a graph from here, okay. If I draw here, then this will turn out to be a kind of a linear relationship between the pressure and the temperature. Okay, so next we have taken it very quickly, and next we will talk about the expansion of solids, where we'll take the extension of wires, we'll take the expansion of surfaces, and we'll take the expansion of volumes of material. We'll talk about all those things in the ensuing lecture, coming lecture. Okay, so hope you enjoy that. And of course, I have, when I do like this, it means I'm coming to an end of my lecture. You question and we try to answer. Okay, we don't have any absolute answers to your absolute questions. No question is absolute and no answer is absolute. Okay, science will go on and on and on only if pertinent questions are asked and dedicated answers are searched. So for now, thank you very much.